Maybe it happened to you like it did to me, that because of the movie Top Gun, one fell in love with the F-14 Tomcat. This beautiful aircraft has had a great impact on the way the United States Navy carried out fleet defense. But today, the concept of variable geometry applied to air superiority is not viable. But why? Thanks to the text of 1000 Annuel Represa from the blog The Flight of the Great Bustard, on which one based this video, we will answer it and also see the application of variable geometry in other types of aircraft, such as the B-1 Lancer, the Tu-22, 1003 or the Tu-160 in this new installment of Aviation World. Variable geometry wings evolved as a solution for the early jet engines. Experiments with wings that could change their geometry on the ground, such as the Messerschmitt P 1101, were conducted as early as World War II. Back then, the first jet engines produced less thrust because they operated at lower temperatures and were generally more primitive. The possibility of using wings with very pronounced sweep to achieve high speed was studied, but it resulted in the aircraft having very high takeoff and landing speeds, making the operation less safe and longer runways would be necessary. The Bell X-5 was the first aircraft capable of changing the angle of its wings in flight. Built in the United States, it was based on the design of the P-1101 captured at the end of the Great War. There's a video of this on the channel for you to look up. But the first mass-produced aircraft with this system was the F-111 Auerbach. The famous F-14 Tomcat derived from it, inheriting the variable geometry wings. In Europe, two major projects were the Panavia Tornado and the ADB version of the Interceptor fighter, and then the ADB version of the Interceptor fighter. And the other project was the Dassault Mirage G, which never went into production. The Soviet Union made several notable variable geometry designs. Among them, we can name one of the first, which was the Tu-148. Then, the ground attack plane Su-17 with its 20 and 22 variants. The Mikoyan 23 and its ground attack derivative Mikoyan 27. And the Su-24. The main advantage is that they can use that wing with variable affliction to find the optimal wing angle for a given speed. With reduced angle swept wings, that is extended wings, more load can be carried and the aircraft will take off and land at shorter distances. It will also be more maneuverable at low speeds, The advantage of the maximum swept configuration is at high speeds and low altitudes, increasing its maneuverability and fuel economy. These are great advantages for fighter planes. But then, why aren't new designs currently being used? That with these systems, there is a great disadvantage: the weight and complexity required to operate this mechanism, which counteract the advantages. Also, this complex and heavy mechanism adds a great amount of mass to the total of the aircraft, and makes the fuselage larger, creating more resistance, which means more fuel consumption. Besides, of course, the place where this mechanism is located could be used to put more fuel tanks. Regarding fighter planes, in close combat, this heavy mechanism with all its gears compared to a fixed wing would result in an unfavorable thrust for the aircraft's resistance, even if the pilot could switch to an optimal geometry just before combat. Changing the wing geometry during dogfight combat would be a great risk, as it would surely lead to a loss of energy, which is the least desirable in these situations. Conditions. This mechanism would also lead the G-force limits to lower values. In the latest version of the F-14-500, the symmetric limit was 6.5 G, while in the F-16 and the F-15, which have fixed wings, are capable of reaching 9 G. Jet engines have become much more powerful than their counterparts from the 60s and 70s, allowing for much higher thrust-to-weight ratios. For this reason, lower takeoff and landing distances can be achieved. This factor almost completely nullifies the main advantage of the variable geometry wing, the greater efficiency at low speed. The more complex a system is, the greater the risk of failure. When the United States Navy chose to retire the F-14 in favor of the FA-18, one of the main reasons was the terribly disastrous flight hour and maintenance ratio. On average, an F-14 required nearly 50 hours of maintenance for every hour of flight, while the F-18 Super Hornet requires 5 to 10 hours of maintenance for every hour of flight. There are also other weak points in this system. There have been occasions when one side of the mechanism or its gearbox has malfunctioned, leaving the opposite side in an asymmetrical wing configuration. While the aircraft could fly in such a situation and land with some difficulty, this clearly shows us a critical point to consider, because enemy fire could occur. Also notice how complex the mechanism is for enemy fire. Also notice how complex the mechanism is for moving the wing load pylons on planes like the Panavia Tornado, the F-111, the Su-24 or the MiG-23 and 27. These pylons move so as not to lose their aerodynamic front. But in other designs, like in the F-14, the Su-17 or the Tu-22-1003, in the fixed section of the wing roots. It's curious, in the fixed section of the wing roots. The case of the 81, a National Aeronautics and Space Administration prototype to study the use of the pivot wing, capable of changing its geometry by rotating a single wing between 0 and 60 degrees during flight, is curious. It was supposed to be a good idea for larger transport planes, but as before, it had many mechanical and aerodynamic problems. There are also other types of aircraft such as the B-1 Lancer strategic bombers, Tupolev Tu-22-1000, and the Tupolev Tu-160, or the Great Interceptor Tu-148, precursor of the design of the Tu-22-1000, which, as we had seen, the minimum swept wing configuration is used for takeoff, landing, and to maintain normal cruising speed at high altitudes. The maximum swept wing configuration is used to be able to reach transonic and supersonic speeds at high and low altitudes, increasing its maneuverability, high-speed fuel economy, and surprise capacity in deep penetration attacks at low altitude. To conclude, the cons outweigh the advantages when it comes to variable geometry wings. There are very significant penalties in terms of mass, operational cost, and complexity. While they may have some advantages at takeoff and can have optimal deflection for each scenario, the disadvantages outweigh the advantages to the point that we do not see modern planes with these types of devices today. Thanks for watching. One, hope you enjoyed this technical explanation. One, if you'd like to support the channel financially, you can do so via Patreon, PayPal, or Mercado Pago. Until next time, one, I'm Marcos, and this is World of Aviation.